Hi, this is Professor Fernandez, and welcome back to Math 205. Today we'll be talking about Lesson 2. In this lesson, we're going to learn about vectors and also the dot product. So let me just run through the lesson preview. We are going to be talking about vectors, which is a concept that we'll use throughout the rest of the course. Actually, say that right here. We're going to be learning how to visualize vectors in this lesson and also doing some vector arithmetic. In particular, in Module 1, we'll talk about foundational concepts, terminology associated with vectors. And then I'll show you through various built-in features of the iPad how we can visualize vectors. Then we will talk about the algebra of vectors. How do we add vectors? How do we subtract vectors? Some of that arithmetic. And then finally, in Module 3, we'll learn how to multiply vectors together. So I put multiplication in quotes here because this is not the same as, 2 times 3 when we multiply numbers. There are two operations for, quote, multiplying vectors. In this lesson, we'll talk about the first of those called the dot product and then discuss what information and insights that provides. I mentioned in the first video that lesson 1 video that I would sometimes after the lesson preview give you some real world connection to the concepts that you'll be learning in the lesson. This is the first of those. So if you have ever, so I'll just mention a few quick things here and encourage you to read this on your own time if you're interested. If you've ever driven by Boston, you might have come across the Zachem Memorial Bridge. So here's a picture over here. Anyway, there's a lot of interesting engineering that is behind this type of bridge. This is a cable-stayed bridge, a specific type of bridge, where the cables come from the top of the bridge and kind of go down to the floor, if you will, the bridge itself. So on the right-hand side is my very crude way to depict what's going on in terms of two particular cables suspended between, connected to the tower, this tower in the middle over here, and the bridge itself. And if you drive by this bridge, you can see in this picture, these cables are taut. There's a lot of tension in them. And that's kind of the idea, to keep the bridge up. So we can think of the tension in these two cables, and we immediately realize that there are two fundamental properties of that tension. One of them is that it has a direction, right? So this T1 over here, this arrow, points in a specific direction. So, the cars driving by over here weigh a lot, and they pull the bridge down. And in doing so, they pull this cable that way. So hence the direction here. The second property of the tension is that it has a magnitude. So there's a certain amount of tension. It's not very little tension because this is a very heavy bridge that's very trafficked. And it's some number. So there's some magnitude, we say, for this force. So those two aspects, the magnitude and the direction of these two arrows, are key features of what we're going to introduce in a minute, what we will call vectors. So I encourage you to read through the rest of this. It's interesting that we can think and visualize and experience vectors in the real world if you drive across one of these cable-stayed bridges or ever visit Boston. Okay, so let's go ahead and move on to the actual math. Now we have a little bit of motivation for it. So the first thing I'll do is formally define what a vector is. So here is that definition. Again, if the page numbers are here, they refer to the page in the Apex Calculus book that's linked to in the practice problems at the end of the lesson notes. So here we go. A vector is a directed line segment. So let's just pause there really quickly. So we're thinking about a line segment. There's a line segment. And then we're going to add a direction. So maybe that way. Except that normally we put the direction at the very end of the line segment. So, you could also call a vector an arrow. But it's a little easier for the purposes you'll see in a minute to refer to it as a directed line segment. Great. So I give you some additional information in these bullet points. So by this, we mean that given points P and Q, we denote with, so this is the notation for a vector, a little arrow on top of something, the vector from P to Q. So that's the directionality. Wherever the point P is, we start there. Wherever the point Q is, we end there. And that's the direction we're moving in. So this might be a point P down here. This might be a point Q up here. and then I want to go in that direction. And this arrow would then be the vector PQ with an arrow. Great. So the second thing is that the point P is the initial point of the vector, and the point Q is the terminal point. We call the magnitude, length, or norm, all synonymous in this context, of the vector, the length of the line segment. So this explains why we called it a directed line segment, so we could find the length of the line. And then we have this terminology. So let me just declutter things here so we can see a bit more clearly. So we will refer interchangeably as the context provides to these three concepts. So if I go back over here, if I'm looking at, if I had a ruler and I could measure, let's maybe try that, a gigantic ruler here, and I could measure this length. I have no units that I can tell, but there we go. This is that long. So that's what I roughly mean by having some sense of the length of a vector. So measuring it, getting a number. It's 4 centimeters long. It's 4 inches long. And again, the notation for that is this double bar is almost like a double absolute value, and then the vector itself, and then the other bar. Sometimes, you might have seen me doing this already. I will do this with the vector, and it's just a little lazy way not to put the other arrow. So this is completely equivalent from a notation point of view. This is notation used more in physics. So it's slightly faster to not put that other arrow. So the last part, next to last part of this definition, if this equals 1. So in other words, if the norm, if the length of the vector is 1, we call the vector a unit vector. So that's, again, just notation. We indicate this with a hat. So the difference between PQ vector and PQ hat is that this one has length equal to 1. This one has length not equal to 1. So it might be shorter or longer than 1 unit long, length not equal to 1. Okay, so that's really the only difference. And then finally, we say that two vectors are equal if they have two properties exactly the same magnitude, length, norm, and the same direction. Okay, so let me draw for you some other vectors and illustrate some of these properties. Actually, we've illustrated most of these on the left here, but here's an example. So I'm going to put in here a line. Let's make it red. And here we go. So this is one vector. Whether or not it's a unit vector, I don't know. Depends on what units, if you will, I'm using to measure it. Am I using centimeters? Am I using meters, feet? But if I duplicate this vector, then I have drawn exactly the same vector. So this is illustrating the notion of what we mean by vectors are equal. These two vectors have the same magnitude. I literally just copied and pasted them. I did not change their length. So check. And they also have the same direction. I did not change the way they face. The moment I change one of these two properties, though, well, before I do that, let me just mention, if I move this around, even though, let's call this vector u, this is u, and let's call this vector v, even though these are different vectors visually, in the sense that, they're in different places, mathematically, do they have the same magnitude? Yes. Do they have the same direction? Yes. So as far as we're concerned, these vectors are equal. And again, I can just move this around, so and I won't change the magnitude of the direction. So one thing we learned from this is that if we translate vectors in the plane, or in R3, however many dimensions you're looking at, translate meaning we just move it around without changing its magnitude, length, or direction, then we're still talking about the same vector. So I could do this, I could just get rid of referencing the second vector. Just do this with the first vector. This is u. This is also u. That's also u. That's also u. It's the same u. And that explains why this definition should make sense. Somehow, if this was u that you're looking at, and now this is some other vector v, that wouldn't make sense. It's the same arrow. Great. So when I, however, go back and do something to change the length or the direction, then that changes the vector. Then we're talking about another vector. So these two vectors legitimately are different vectors, this u and this v, because in this case they have different directions. Great, so let's do some quick examples here just to get familiarized with some of these concepts. So let v be the vector in the plane with initial point P and terminal point Q. So first, let's plot the vector. All right, so we're starting here just in R2. We're not doing anything in R3 for now. So I'm going to go to the point 1, 1. That's my point P. And then I'm going to go to the point 2, 3. That's my point Q. And then I'm just going to draw the arrow from P to Q. So that is the vector V. Okay, so far so good. Number 2, find the magnitude of the vector. So magnitude of the vector. So what I want to do is I want to find the length of this line segment. So PQ vector length equals, and this is where I'm just going to zoom in a little bit so we can do some more work here. So what's going on here? Well, this is a right triangle that I can generate. So I'm going to erase V here. And there we go. This is my attempt at drawing two straight lines. And what do I see for the base of this triangle is? Well, this has base length 1 because it's 2 minus 1. And then over here, this has base length 2, 3 minus 1. So I have a right triangle that looks like this, 1, 2, and then by the Pythagorean theorem, this would be the square root of 1 squared plus 2 squared, which is square root of 5. Great. So we have found the length of the hypotenuse, which is the length of the directed line segment from P to Q. In other words, the length of the vector PQ. So this on the right-hand side is square root of 5. Okay, great. So we have the first two of these examples done. And then number 3, is the vector a unit vector? So recall that unit vector means that the length is 1. So the answer is no, since length of PQ is not equal to 1. Great. So again, this is just a very quick example to illustrate some of these concepts. But the other thing that I want to talk about with this example is what it teaches us about vectors. So we actually do learn something from this example if we think a little deeper into what's going on, and specifically what I just did over here with these lengths that led us to be able to calculate the vector's length. When we think about it, right, what did we do to draw this vector? What I did first was I drew the point P, and then I drew the point Q, and I connected them with an arrow. But what I could have done separately, differently, is I could have started with the point P, and then I could have said, oh, Q is at x value 2, as opposed to P at x value 1. So I'm going to move 1 unit to the right. Move 1 unit to the right. And then I could have said, oh, the terminal point has y value 3, and that is 2 units up from 1. So I'm going to move up by 2 units. 2, 3. And then I could have said, oh, P is, the vector PQ starts at P and then ends where I just ended up with my horizontal and vertical movement. And that's my vector PQ. And you can see that I obtain exactly the same vector a different way from what I did originally. So these numbers, this number 1 here and this number 2, somehow helps me to construct the vector PQ. And the somehow is how I just illustrated. It tells me how far in the x direction to move, and it tells me how far in the y direction to move to get to the terminal point that partly defines the vector PQ. So these numbers 1 and 2 have special meaning, so they're called the components of the vector. So that's the next definition down here. So let's take a look at this definition. This is about the components of a vector. So suppose we're going to do things in R3 now. It's analogous in R2 or higher dimensions. Suppose I have a point P, which is x1, y1, z1, and a point Q, x2, y2, z2. Then we say that the vector V, which we're defining as the directed line segment from P to Q, has these properties. It has an x component, it has a y component, and it has a z component. So each of these then is defined in terms of the differences of the respective components of P and Q. So the x component is the change in the x values. This is the change, the y component is the change in the z values. And the z component is the change in the, the y component is the change in the y values. Z component is the change in the z values. So I'll actually write that here in delta notation, just in case that helps it click a little easier. And then there's new notation that's introduced by this definition. So here's the vector v, that's the notation we know with the arrow. This is new notation. So here on out, when we see brackets, that is denoting a vector. And when we look inside the brackets, everything between the commas is giving us the components of the vector. And at least since we'll spend most of our time in this course in R2 or R3, this would be a vector in R3. What I've just drawn here is a vector in R3. And this is what a vector would look like in R2. So it is a vector in R2. In other words, the first number that you see in these brackets is always going to refer to the x component of the vector. It will tell you how far in the x direction from point P to go. And then the second number is the y component. It will tell you how far from there to go in the y direction to get to the terminal point of the vector if we're in R2. If we're in R3, then wherever you got to, you now have to go a little bit further yet, this time in the z direction, to get to the terminal point of the vector in R3. Okay, great. So last little bit, the next video will cover module 2. Last little bit that I want to mention is to give you some examples of this component work in action. So let's go back to the example that we just did, 2.1, and then just connect things with this component view. So the vector that we had obtained there is here. This is the vector PQ, which I'm just going to call V now, PQ vector. And I can write it down now with this new definition based on its components. We had identified now, looking back, its components, how far to go in the x direction from the initial point, and then how far to go from there to the terminal point. We had identified its components as 1 in the x direction and 2 in the y direction. So we can write the vector in component notation as 1, 2. So this illustrates visually what this definition that we just talked about really means, definition 2.1.2, because if I were to tell you, instead of giving you the information up here that I did about the initial and the terminal point of the vector, if I gave you the components of the vector, if I told you v is the vector with components 1 and 2, then, actually it goes back to the first definition that we talked about. I have specified the vector. I actually don't need to tell you where the initial point is, because this vector has a certain magnitude. Let's calculate its norm. Well, it's the square root of 1 squared plus 2 squared. Why? Because remember, 1 was the base of this triangle and 2 was the height. So this is the magnitude of the vector. And then 1, 2, this specifies a certain direction, right? If we realize that this is the x component, this is the y component, I could, for example, look at the slope, y over x. So this vector v, or the line v generates, has slope 2 over 1, which is 2. We can see that from this picture, but we can also see that without needing a picture from just the components. Remembering again that this is the y component, this is the x component, and slope is rise over run. So in other words, by giving you just the component form of the vector, which is this, you can extract the magnitude and the direction of the vector. And as we said in the first definition, two vectors are equal if they have the same magnitude and direction. So, this is somewhat amazing. We have now gotten to a point where we don't need the initial or the terminal points anymore. I don't need to give you that information to give you the vector, because I now have the magnitude and the direction, and as we had talked about earlier, you can move arrows around the plane as long as you don't change the direction or length. They're the same arrows, they're the same vector. So the combination of these two definitions is what gets us to this new place where from here on out we will just dispense largely with the need for P and Q, the initial and terminal points of a vector. And we will move just toward specifying vectors by knowing their components. Again, going back to this idea that from there we can extract very easily the length, and we can also extract some version of the direction. I illustrated that for R2. For R3, it's a little bit easier to draw, but you can still conceptualize this. If you drew a vector in R3, it points in a certain direction. And if we moved around that vector in R3, like we talked about earlier, it would still be the same vector, as long as we didn't change its length. Okay, so this is all I want to do for the first module. So a quick recap. From here on out, parts of this definition will remain. We are still talking about the norm of a vector, and that's a length. We're still talking about unit vectors with a special hat notation, and we still have a notion of equality of vectors. We have kind of been able to get rid of the notion of needing an initial and a terminal point to define a vector. That may still be useful in certain contexts, so we won't get rid of it altogether. But we've been able to get rid of it, in a sense, by moving to the component version of a vector. And the components of a vector, initially we defined as the difference in the components of the initial and terminal points. That's what this says. But now we're thinking kind of opposite. We're thinking if I just give you the components of a vector, that is the vector. I can calculate the magnitude from there, and I can certainly give you information about the direction in one way or another. Great. So in the second module, we will talk about how to do arithmetic with vectors, and then we'll start setting the stage for talking about dot product in the third module. See you then.